Good day everyone. Good day sir. I am Joyce Dian B. Sombrero from Psychology 1B. For today, we will be discussing about the application of symbolic logic to switching network together with Ms. Soriano. But before that, we will be first tackling about how a computer works. Do you know how a computer works? All computers use a logic system devised by George Boole. The switches inside a computer chip can be arranged into a switching network or a system of gates delivering logical results. The most fundamental logic gates are called AND, OR, and NOT gates. The application of logic to electric circuits was pioneered by Claude E. Shannon of the Massachusetts Institute of Technology and Bell Telephone Laboratories. The idea is to simplify circuits as much as possible by finding equivalent circuits in much the same way as we find equivalent statements. So, what is switching network? A switching network is an arrangement of wires and switches that connects the two terminals. So there are two types of switch, the closed switch and the open switch. A closed switch permits the flow of current, whereas an open switch prevents the flow. As you can see, the first picture illustrates the open switch and the second picture illustrates the closed switch. One can also think of a switch as a drawbridge over a river controlling the flow of traffic along a road. That is shown in figure 2. The letter P on it demonstrate that the switch can be a drawbridge between the river. Two switches can be connected in series in line from left to right as shown in figure 3. In this network, the current flows between terminals A and B only if both switches P and Q are closed. So, the question is, can we use logic to describe circuits? In considering such a problem, let P be the statement switch P is closed and let Q be the statement switch Q is closed. If P is true, then the switch is closed and the current flows. If P is false, then the switch is open, the current does not flow. Thus, the circuit of figure 2 can be associated with the statement of P. When two switches are connected in series, as shown in figure 3, the current will flow only when both switches are closed. Thus, the circuit is associated with the statement P and Q. On the other hand, in figure 4, current will flow when either switch P or switch Q is closed. The switches are connected in parallel and the statement corresponding to this circuit is P or Q. So what about the statement not P? This statement corresponds to P apostrophe, a switch that is open if P is closed and vice versa. Switches P and P apostrophe are complementary. Series and parallel circuits can be combined to form more complicated networks as shown in figure 5. The network there corresponds to the statement P and Q or R. If we think of the switches as drawbridges, we can see that we are able to go from A to B when both P and Q are closed or when R is closed. Now, all compound statements can be represented by switching networks. When switches open and close simultaneously, the switches will be represented by the same letter and will be called equivalent.
So we have here an example for constructing networks. Example 1. Construct a network corresponding to the statement quantity P or R and quantity Q or R. This figure on the left side corresponds to P or R, while this figure on the right side corresponds to Q or R. We can notice that these two circuits are parallel by judging their switching network diagram. These two parallel circuits are connected in series to correspond to the connective OR, which joins the two statements P or R and Q or R. The network associated with a given statement appears in figure 6. In figure 6, we can see that the two parallel circuits A and B are connected, and the current in this network will flow from A to B whenever the statement quantity P or R and quantity Q or R is true. Complementary. In the design aspects of switching network, it is sometimes necessary to require that one switch to be open while another remains closed. That is, for the switches to be complementary. Two switches are said to be complementary if one switch is open and the other is closed and vice versa. Thus, if one switch is P, the complementary switch will be labeled P'. So for two switches to be complementary, it should be considered that the switches are of different orientations, closed or open. If one is open, the other one should be closed. And if one switch is P, the other one should be P'. Equivalent electrical networks. Two electrical networks are said to be equivalent if they have the same electrical properties concerning the flow and non-flow of current. This means that the equivalent electrical networks have the same electrical properties about the flow and non-flow of their current. Therefore, it is a must to always bear in mind the laws and properties concerning equivalent simple and compound statement. We have here an example 1. Find a network equivalent to the one given in figure 2.7. Note that the dashed line indicates the path of the electrical flow. The current in this network will flow from A to B whenever the logical statement quantity P or not P and quantity Q or not Q is true. The figure 2.7 shows that network diagram of the electrical circuit P or not P and Q or not Q. The dashed line also represents the flow of the current. So we are tasked to find a network equivalent to figure 2.7. In doing so, we need to obtain statements and supports or reason in order to justify our process of identifying its equivalent networks. We have here the solution. A network equivalent to figure 2.7 can be obtained as follows. First, the statement P or not P and Q or not Q in the statement that describes the circuit given in figure 2.7. Second, the statement that describes the circuit given in figure 2.7 is equivalent to T, and T according to the complement law. Third, the statement derived based on the complement law is equivalent to T according to the identity law. Therefore, the statement P or not P or Q or not Q is equivalent to T. We have here another example. Example 2. Obtain a network equivalent to the network given in figure 2.8. Figure 2.8 shows the network diagram of the statement P or not P and Q or P and not Q. For the solution, the current in this network will flow from A to B whenever the logical statement P or not P and Q of P and not Q is true. Note that although figure 2.8 shows a pattern of open and closed switches, a number of different patterns that will allow current to flow from A to B are possible. The several patterns are illustrated in the following diagram. First diagram from the left, this diagram here shows the flow of current from A to B whenever P is true. The current flows from A to B passing through the P here in the upper part of the network diagram. Second diagram. This diagram here reveals the flow of current from A to B whenever the statement not P or Q is true. The current flows from A to B passing through the P' and Q here in the middle part of the diagram. Third diagram. This diagram here shows the flow of current from A to B whenever the statement P or not Q is true. The statement flows from A to B passing through the upper and lower part of the diagram wherein the P and Q' are located respectively. These three diagrams here are the equivalent electrical network for figure 2.8. We have here another example. Example 3. Draw a switching network corresponding to the compound statement P or not Q or Q or not P or Q and not Q. Also, find an equivalent network simpler in design. So we are asked here to draw the switching network and find an equivalent network which is simpler. Solution. The switching network described by the preceding logical statement in this diagram. In this figure, we have labeled here the constituent statements of the compound statement given. The P or not Q here in the upper part, the not Q here in the middle part, and the not P and Q here in the lower part. This figure is the switching network that corresponds to the compound statement P or not Q or Q or not P or Q and not Q. To find the statement equivalent to this compound statement, we proceed as follows. For our first statement, we have here the statement P or not Q or Q or not P or Q and not Q, which is the statement that describes the circuit. Second statement shows that the statement that describes the circuit is equivalent to P or not Q or Q or not P and not Q according to the associative law. Third statement tells that the statement derived based on the associative law is equivalent to P or T or not P and not Q according to the complement law. Fourth statement shows that the statement derived based on the complement law is equivalent to T or not P and not Q according to the identity law. Fifth statement reveals that the statement derived according to the identity law is equivalent to T and not Q, basing again on identity law. Sixth statement shows that T and not Q is equivalent to not Q according to the identity law. Therefore, the compound statement P or not Q or Q or not P or Q and not Q is equivalent to not Q. Thus, the complicated network diagram shown previously is just equivalent to the diagram of not Q. And that ends our reporting for the switching networks. Thank you for listening.